Man's ancient and still unbeaten enemy from the dawn of history to this moment and now is still hunger. His never-ending war against the forces of nature still goes on to produce enough food for all human beings everywhere. Exhausted, starving land in need of nourishment, ground grown barren with the harvestings of countless seasons. Topsoil washed away by floods, blown away by the winds, soil eroded slowly by time and the elements. Crops laid waste by plant disease and blights, devoured by plagues of locusts, grasshoppers, insect pests of many kinds. These are man's enemies, and this is a war that is not limited to one nation or one continent. It transcends political systems and ideologies. It knows no boundaries. Many of mankind's wars have been fought for food, for land and resources, but ultimately for bread. Today, man has a new ally which can join one nation to another in common cause. The ally is science. Plant breeders and pathologists in the United States and in all countries have been experimenting for many years with food plants. These men work with nature instead of against her, breeding new plant varieties that are resistant to certain kinds of plant disease. It took decades of patient breeding and crossbreeding to find the variety of wheat that could resist a disease called wheat rust, which was destroying wheat crops everywhere. Atomic energy can shorten this lengthy process of crossbreeding for new varieties. In an outdoor laboratory in the United States, plants are grown while exposed to the gamma rays given off by radioactive cobalt. Before working in this field, a scientist must first operate a windlass to lower the radioactive cobalt into the ground. A Geiger counter is carried so that the amount of radiation can be checked. Gamma rays from the radioactive cobalt have the power to change those microscopic elements in a seed which determine the nature and characteristics of the plant itself. Corn, for example, is exposed to radiation to see what the effects may be on future plants. In this way, atomic energy is now providing stronger disease-resistant and weather-resistant varieties of oats and other crops, leading to higher yields of food. Ears of corn grown in the gamma ray field are later studied in the laboratory. A particular kernel which shows a change due to radiation is removed for planting. Although such research is still in its early stages, atomic energy is already accelerating the work of plant breeders immeasurably. Since 1948, the United States Department of Agriculture, in cooperation with the Atomic Energy Commission, has operated a special greenhouse building for agricultural research with radioisotopes. The ability to detect the presence of radioisotopes with a Geiger counter makes it possible to employ them as tracers in plant nutrition studies. For example, experiments with radioactive calcium, iron, phosphorus, and zinc have already established basic facts that show how different food plants make use of these elements in varied types of soils. In a typical study of this kind, the soil is mixed with a radioisotope such as radiocalcium carbonate. A specific amount is put into a blending machine where it is well mixed with the soil. Later, seeds are planted in cans of soil containing the radioactive calcium carbonate. Ten days later, the plants have grown to medium height and are ready to be harvested and studied. The beakers full of the cuttings are placed in an oven for drying. Next, the dried leaves and stems are put through a grinding mill where they are reduced to powder. After the powder has been compressed to form tube-shaped briquettes, a special apparatus which works in the same way as a Geiger counter is used to measure their radioactivity. In addition to the briquettes, chemical samples will later be examined. The radioactive atoms of calcium carbonate which were mixed in with the soil may have been absorbed by the roots of the plant as nourishment in producing leaves and stems. If so, these calcium carbonate atoms are now in the briquettes and chemical samples. Since they continue to give off rays, the counter will tell approximately how much of the calcium carbonate was used by the plant in growing. Information like this is of great value in producing more efficient fertilizers for farmers. Until atomic energy came to the aid of agricultural researchers, it was not possible to determine with any degree of exactness the nutritional needs of a particular crop. As a result, fertilizers were often wasted. In the future, farmers will be able to use fertilizers more economically for the production of more abundant and finer crops. Atomic energy can also preserve crops after they have been harvested. These potatoes can be preserved for as long as 2 years without refrigeration. The potato at the left, still fresh and firm, was irradiated 6 months before this picture was taken. The one at the right was not. This process, which can be applied to meat, fish, and other products without injuring the food, may revolutionize food preservation. Radioisotopes can also be used as tracers in learning how domestic animals utilize specific elements in food. In this experiment, a hen is fed a harmless solution of radioactive calcium-45 and radioactive phosphorus-32. The next day, an egg which was laid by the hen is brought to the laboratory for analysis. The purpose of this experiment is to try to determine how the hen absorbs calcium and phosphorus and builds them into the various components of the egg: the white, the yolk, and the shell. So that each can be analyzed separately, the egg is divided into its 3 parts. The 3 beakers are then placed in an oven for drying. Later, they are removed, and the scientist prepares to analyze them for radioactivity. Those atoms of radiophosphorus and radiocalcium which were absorbed by the hen as food will continue to give off rays, and those which the hen has utilized in producing the egg will be present in the 3 parts of the egg in varying amounts. They will be readily detected and measured by the counting apparatus. Experiments of this kind will help scientists to learn more about the life processes of farm animals, and ultimately to devise diets especially designed to improve the quantity and quality of such food products as eggs, milk, and meat. But the productivity of a farm today is dependent too on the efficiency of its machinery. And here again, atomic energy is already working for man's good. In the factory where this farmer's tractor was made, the engineering laboratory employed radioisotopes to test the quality of the piston rings used in its engine. The piston rings used have been made radioactive in advance of this test. For protection, they are stored and transported in lead containers. One of the radio iron piston rings is attached to the piston of an automobile engine. The problem is to measure how well the piston ring will wear. When the engine is running, the piston ring rubs against other metal parts, causing minute particles of the ring to wear away due to friction. These radioactive particles accumulate in the engine oil. After the engine has run for several hours, a sample of oil is drained off. Any radioactivity in this oil must come from particles which were worn off the radioactive piston ring while the engine was running. By using an instrument similar to a Geiger counter, the radioactivity can be counted and approximately measured. The higher the count of radioactivity, the greater the wear on the piston ring. Before the use of radioisotopes, such tests for wear were made by slower and far less accurate methods. The factory which made these rubber tires employs radioisotopes in tests for wear and durability. Radioactive sulfur is used effectively in carrying on experiments with the vulcanization of rubber. Some of the cast metal parts of this tractor are superior to those used in the past thanks to radioisotopes. Flaws and imperfections in machine parts can be easily detected by a process called radiography. The gamma rays given off by radiocobalt reveal flaws in much the same way that X-rays reveal defects in teeth. The radiograph is, in effect, a picture of the metal part with flaws showing up as dark areas. To make a radiograph, the machine part to be tested is taped to a holder containing a sheet of X-ray film. Then the radiocobalt is removed from its lead container and is set in place to expose the X-ray film. Gamma rays from the radiocobalt pass through flaws more easily than through perfect areas of the metal and show up on the developed picture. In this way, imperfect parts can be discovered and scrapped, and stronger, longer-lasting farm machinery is the result. Without fuel, tractors cannot work for the farmer, and atomic energy may someday play a part in the production of synthetic gasoline and oil. In the laboratories of oil refineries, chemists are using radioactive carbon-14 as a tracer in extensive experiments with synthetic gasoline. These can be of great importance for the future because oil supplies are not limitless. Furthermore, the world's fuel needs are not static. They are on the increase as industrial development spreads to more areas of the world. Oil wells run dry eventually, and someday, perhaps not in the immediate future, the world's oil resources will be exhausted. But oil, of course, is not the only source of energy. What about other fuels? There is coal, and the present supply is still adequate. But even the world's supply of coal is not endless. Any estimate of coal resources must again take account of expanding energy needs everywhere in the world. Some mines have already exhausted their richest veins of coal. Others have become too dangerous to be worked. The time has come for all nations in the world to begin to think of the future. The use of atomic energy for power offers at least a partial answer, and it is at this moment a reality. Now, let us see how a nuclear reactor works. This is an atomic pile at Los Alamos in New Mexico. It is called a water boiler reactor. The chain reaction that takes place in an atomic bomb is instantaneous and causes an explosion. But in a nuclear reactor such as this, the chain reaction is slowed down and controlled. From a control room, it can be brought to power within a few minutes and can be smothered even more quickly. The The operator adjusts the dials to bring the reactor up to power, and the control rods begin to rise. A light flashes to warn workers that the pile is on. Later, when it is desired to smother the reaction, the operator presses a switch to lower the control rods. Now, let us look at another type of reactor. This one is in Idaho, in the western part of the United States, and is called the Experimental Breeder Reactor. Designed and built by United States scientists, this reactor is the world's first operating atomic power plant. It has been producing usable electricity since 1951. This type is one of 5 basic kinds being developed by the United States Atomic Energy Commission in an intensive experimental program to determine which designs are best. The time is not too distant when they will be available for large-scale production, thus bringing atomic power to homes and factories. The principles by which this reactor works are not complicated. The heat generated by the pile is picked up by a liquid metal which in turn is used to generate steam from water. The steam drives a turbo generator which produces 170 kilowatts of electric power, which is sufficient to operate the pumps, lights, and machine shops all over the building. This technician is preparing to make the changeover from the outside power line to the line coming from the reactor's own generator. As the switches are turned, the changeover is made. The lights, momentarily out, go on. For the first time in history, atomic power is providing light and energy for the benefit of man. The people of the United States and their president, Dwight D. Eisenhower, do not believe that the development of atoms for peace is a one-nation job. On March 13, 1955, students from 19 countries, representing the continents of Europe, Asia, Africa, South America, and Australia, arrived in the United States to attend the newly opened School of Nuclear Sciences and Engineering near the city of Chicago. This day will long be remembered by peoples everywhere. It marks the beginning of an extensive, permanent program of educational exchange applying the knowledge of the atom to the betterment of mankind. Because all men everywhere, all nations, must work together if famine and disease are to be conquered. Barren, unproductive land must be reclaimed and renewed. More of the Earth's surface must be utilized for food production. The domestic animals on whom human life depends must be well fed and not starving, sick, and undernourished, fighting for survival. On Labor Day 1954, President Eisenhower initiated the construction of the nation's first full-scale nuclear power plant at Shippingport, Pennsylvania. Although atomic power will not answer the world's problems next week or next year, it is a strong beginning and a definite promise. The United States hopes that this plant will be merely one of many that will someday be constructed in all parts of the world. There is little doubt that ultimately they will produce power as cheaply as it can be produced by present fuels. But most important, it will be possible to provide power in isolated areas of the world, remote regions to which sufficient quantities of present fuels cannot be transported. The atom is small, but its energy is great. Its power for man's good is as vast as its power for destruction.